So, if you've got solar panels, you've probably noticed something a little weird. Even on a perfectly clear, sunny day, your power output can be all over the place. To figure out why, we're going to follow a single ray of light on its amazing and kind of difficult journey from the sun all the way down to your roof.
Right. Here's the big puzzle we're trying to solve. You look outside, you see clear blue skies, a super bright sun, but your app shows your power generation is on a total roller coaster. So what gives? Well, as it turns out, it's not just about clouds. It's a story of physics, a little bit of geometry, and the incredibly challenging trip every single photon has to make to get to us.
Okay, let's start way out in space. Before a single photon even touches our atmosphere, it's packing a punch that scientists have a name for: air mass 0, or AM0. That's a whopping 1353 watts for every square meter. But by the time that same light gets to the ground, even on a perfect day, it's down to about 1,000 watts. That means it loses almost a third of its power just getting through the front door.
To really get why that power disappears, we have to look at what that light is traveling through. It's not just empty space between the sun and your solar panel. No, it's a journey that is absolutely packed with obstacles.
This journey really boils down to two huge challenges. First, you've got the atmosphere itself. And second, there's the fact that the sun is a constantly moving target. Let's tackle the atmosphere first, shall we? All right, first up, the Great Atmospheric Filter. Our atmosphere is obviously essential for, life, but for incoming sunlight, it acts like a giant, invisible obstacle course.
Scientists have a really cool term for this: air mass. So when the sun is directly over your head, its light takes the shortest possible path through the atmosphere. We call that air mass 1. But as the sun gets lower in the sky, its light has to slice through way more atmosphere, which increases the air mass number and filters out more and more of its power.
And this effect is way more extreme than you might think. Right at noon, when the sun is high, light zips through a pretty thin slice of air. That's our air mass 1. But check this out. In the early morning or late afternoon, when the sun is near the horizon, that light has to travel sideways through more than 10 times that amount of atmosphere. That is a ton of filtering. So here's the really crucial part. The atmosphere doesn't just block light. You've got gases like ozone and water vapor that literally absorb certain colors of light. Then you've got air molecules that scatter other colors, especially blue light. And, fun fact, that's actually why our sky is blue. All this scattering creates what we call diffuse light, which means light is hitting your panel from all directions, not just in a straight line from the sun.
Okay, on to challenge number 2, chasing the sun. See, your solar panel is bolted to your roof. It's fixed, but its power source? It's on the move all day long. Now, to track the sun and figure out why its position matters so much for a solar panel, you really only need to know two things: how high up it is and what its compass direction is.
First up is the elevation angle. That's just a fancy way of saying how high the sun is in the sky. It starts at 0 degrees right on the horizon at sunrise, climbs up to its highest point at solar noon, and then sinks right back down to 0 at sunset. This changing height is the #1 reason your power output graph looks like a big bell curve over the day.
And the other piece of the puzzle is the azimuth angle. Really, that's just a fancy term for its compass direction. It moves from east to west as the day goes on. You put elevation and azimuth together, and you can pinpoint the sun's exact location in the sky at any second of the day.
So, let's say our photon has made it through that atmospheric gauntlet, and we know the sun's always on the move. The big question then becomes, how in the world do we position our fixed solar panel to catch as many of those photons as we possibly can, day in and day out? The physics behind this is actually super simple. To get the most power, you want the sun's rays to hit your panel dead on, at a perfect 90-degree angle. It's kind of like catching a baseball. You get the most impact when you catch it right in the pocket, not when it just glances off the side of your glove. Same exact idea for photons. Or, hey, think about it like this. Imagine you're trying to fill a bucket with a fire hose. If you hold that bucket straight on, perpendicular to the spray, all the water goes right in. But if you tilt the bucket, the water just glances off and spreads out, and you catch way less. A tilted panel does the same thing to sunlight. It spreads that energy out, which reduces the power you get per square inch. So what does this all mean for you, practically speaking? Well, it boils down to some pretty simple rules of thumb. If you're in the northern hemisphere, your panel should face south. In the southern hemisphere, they should face north. And for the best possible performance all year long, the ideal tilt angle for your panels should match your location's latitude. It's a really elegant solution to a pretty complex problem. All right, let's wrap this up and put all the pieces of this incredible photon journey together.
So, to recap, what have we learned? First, that journey through the atmosphere really matters. The air itself acts as a filter and saps a ton of power. Second, the sun is a moving target, and we can track it with its elevation and azimuth. And finally, the angle is everything. Your panel has to be positioned to catch those rays as directly as it can.
And that kind of leaves us with a final, pretty interesting thought. We spend a lot of time and money trying to make solar cells just a few percentage points more efficient. But as we've seen, just getting the angle right can have a massive impact on how much power you generate. As our technology gets better and better, you have to wonder, how much more important will it be to optimize for this incredible journey of light?